Hi folks, just a wee extra video on first principles differentiation, just to show you a couple of results, useful results. The limit cos x minus 1 over x is equal to 0 as x tends towards 0, and then the limit as x tends to 0 of sin x over x is equal to 1. Now I'll link in the video proofs to each of these, but you don't need to be able to prove them. Just they're going to be useful results to us when we try our next example. So in your notes, this is the fourth example where we're going to try and differentiate using our new definition of the derivative. So we're asked to differentiate this, so x squared plus cos of x. And just bear in mind this in your notes as well, but if we have two functions added together like we do here, the sum of two functions, if we want to differentiate this would just be the same as differentiating each part separately and adding the derivatives together. So it's a nice wee useful result we could use as well. But again, if we're going to work out f dashed of x, we first start off with our definition of the derivative. So the limit as h tends to 0 of f of x plus h minus f of x all over h. Continuing on, in this case we're just inputting x plus h like we have done in previous examples, so we end up with the limit as h tends towards 0 of x plus h all squared this time plus cos of x plus h, and then this is minus f of x, which is this, so that's subtract x squared, and remember it's subtract all of this, so it's take away that and take away cos x, so I'll just distribute this negative out to that, and that's all over h. Continuing down, so that's a limit as h tends towards 0. I'm going to expand this bracket, and I'm going to expand this this addition using our addition formula, this trig function. So we end up with x squared plus 2xh plus h squared. And then if we use our addition formula, we get plus cos x cos h minus sin x sin h minus x squared minus cos x. And you'll see straight away again, like what happened previously in the other examples, our x squared term is just going to cancel itself out. And this is all over h. I might start using a ruler for that bit. Okay, but continuing on, the limit as h tends towards 0. Now, like I said, the x squareds will cancel each other out, so what we're left with is 2xh plus h squared. Then we have a cos x cos h, and I'm going to group the other cos together with that, so I'm going to end up with, just reordering this a wee bit, cos x cos h, then the minus cos x, then minus sin x sin h. Okay, and that's all over h. Continue on, just again looking to simplify this top line so we can easily work out what this limit is. Now, not really much I can do with the 2xh and the h squared. They're fine because they'll cancel with that h in the bottom anyway, so I'll just keep them there for now. 2xh plus h squared. Now for this bit, the part involving the cos x's, I can actually take cos x as a common factor out of these two terms, and you'll see that will give me a useful result. So cos of x, and in the bracket goes cos h minus 1, and then minus sin x sin h. and that is all over h. Okay, now at this point, if we look at the first two terms, these two terms contribute towards the derivative of that first term. What I'm really going to do is I'm going to take each part of this large fraction and just split them into separate fractions. And what you'll see is, based on the two results we had before, we're going to have those two results coming out as well. So continuing down, that's the limit as h tends to 0 of this part over h. Now in this case the h is just going to cancel, so we get 2x plus h, that's me just cancel those h's, and then plus the limit as h tends to 0. I'm just distributing this limit across of this now over h, so cos x. Now I'm going to do something a bit fancy here. I'm going to take the cos x out and just put the cos x minus 1 over h, just so we can easily see that's the result we looked at last time. Cos h minus 1 over h. Bear in mind, if I was to multiply these two things together, we'd get that all over h. But if I just bring the cos x out of the side, I can easily see that result in there. And then that's minus sine x. Do the same thing here. I'm going to keep the sine x outside, and I'm just going to put the sine h over h. That should be, I'll change that in a second. Sine h over h at the end there. And just bear in mind, I've forgotten my limit. So that's also the limit as h tends to 0 here. Okay, so a nice wee thing you can do with your limit, just spread it out. You can distribute it among each term here. So, continuing on, we know the limit of 2x plus h as h tends to 0, so if that h went to 0, I'd just be left with 2x, which is what I expected that first term to come out to be. So x squared, if I differentiate, becomes 2x. That's fine. Now, if we remember back to our two previous results, if I have cos x minus 1 over x, that goes to 0 for the limit x tends to 0. So this part in the bracket actually just goes to 0. Now, because that's multiplying cos x, that will also go to 0, and that whole term just becomes 0, just disappears. And then for the final term, the limit as h tends to 0, sine x multiplied by sine h over h. Well, sine of something over itself, sine x over x or sine h over h, as a limit as it tends to 0 is equal to 1. So this part in the bracket, I might do this a different, I'll do green. So this part tends towards 1. Okay, so when that tends towards 1, I'm just left with the sine x, the negative sine x really there. So 2x minus sine x. Okay, that's sine x. There we go. Okay, and then if I was to use my rules from higher to differentiate this, yeah, 2x minus sine x is what I would get. So happy with that. So just reducing these couple of results which are quite useful in this case. Like I said, there are proofs for these, but you don't really need to know them this year, but I'll link a couple of videos for you.